Okay, a good example of an approach that takes into account both the Q estimation and the uncertainty regarding the estimation is upper confident bounds action selection, UCB. And this is a very powerful exploration strategy that has some nice theoretical guarantees. We'll discuss those also. So the main idea behind UCB is that the action at every time step is selected according to is set to the action that maximizes the current Q value estimation plus some uncertainty bonus. So we are selecting the action with the highest Q value, but also we take into account some estimation uncertainty. How do we evaluate that uncertainty? We add some uncertainty bonus to the Q values, which is C, some constant. This is a parameter for controlling the degree of exploration, multiplied by the square root of the logarithm of the number of time steps we've been to a specific state, to this state, or that we made this, the decision process so far, over the number of times that we actually selected their specific action that we are now evaluating. So this kind of provides a bonus in the value estimation for underexplored actions. Okay, so each time a specific action A is selected, the uncertainty is presumably reduced because we have another sample for that action, right? So the number of times that action was selected is incremented by 1, and since it appears in the denominator, the uncertainty term decreases. Yeah, that makes sense. On the other hand, each time an action other than A is selected, T, the number of time steps we actually played this process, increases, but NTA does not. Because T appears in the nominator, the uncertainty bonus increases. The use of the natural logarithms mean that the natural logarithm here in the nominator means that the increases get smaller over time, but are still unbounded, so it can still go to infinity. So we will eventually visit each one of the actions infinitely often, but with diminishing frequency. I mean, those that are not greedy actions. All actions will eventually be selected, but actions with lower value estimates or that have already been selected frequently will be selected with decreasing frequency, as I just said, over time. Okay, so let's see how this approach works. So by the way, I didn't include it here, but UCB, this algorithm has some very nice theoretical guarantees regarding the let's say, the suboptimality performance that will incur while learning. So we'll visit these bounds later, I think, when we discuss imitation learning. Okay, so let's see how UCB performs in practice. So again, going back to the example problem that we've seen previously. Again, we have k different bandits, k equals 10. The action space is between 1 and 10. The probability, the reward distribution, is again a normal distribution with some mean and a standard deviation of 1. Again, the maximum Q value the maximum Q star value, the maximum mean, equals to 3, and this is with action number 3, if I remember correctly. Alpha, the learning rate, is set to 0.1 for epsilon greedy, and for UCB, the C parameter, hyperparameter, is set to 2. And you can see that UCB can indeed outperform an epsilon greedy approach. And by the way, UCB also guarantees infinite open visitations, unlike the optimistic initialization approach.